in this lesson, we're again continuing to look at rolling without slipping, and we're going to be looking at rolling down an incline. Now we're going to consider the comparison of the movements between three objects, and specifically we're going to let them have the same mass, so we're not going to give a mass advantage or disadvantage. They're going to have the same radius, so same R value for each of them. The only thing that's different is going to be the distribution of the mass within the object. So the hoop, as we see here, has the largest rotational inertia, mr squared, right? Because most of the mass is as far away from the center point of rotation as it can get. The disk has 1/2 the inertia of the hoop because the mass is closer to the center, and mass closer to the center is easier to rotate in a circle. And here, the sphere, we can see, has the smallest rotational inertia, 2/5 or 0.4, so 0.5, 0.4 mr squared, and the mass is distributed three-dimensionally around the center of mass point, so more of the mass is now permitted to be closer to the center. So the total kinetic energy, as we saw from our last example of rolling down the incline, where we calculated the acceleration was the 2/3 g sine theta, the total energy is shared between the rotational kinetic energy and the translational kinetic energy. So all three of these objects we're going to give the same mgh at the top, and that mgh is then going to get shared, as it says here, into rotational and translational. So 1/2 I omega squared is the rotational, so my v squared on r is my omega squared, so you can get that in there, right? 1/2 I omega squared plus 1/2 m v center of mass squared, and we are simply going to take the I values. So I'm going to take the I value here, and I'm going to substitute in the three I values, and that's all that is shown here in the algebra below. So the three I values are plugged in. We do the algebra, and look what pops out. Well, let's look at the disk, because we kind of know that result. The disk that we just solved for, the accelerations, was 2/3 g sine theta. Well, here's your 2/3. The translational kinetic energy, 2/3 of it goes into translation. 1/3 goes into rotation. And please put in your notes, because I do not want to see you become too complacent in your fractions. Because if we look at the hoop is 50% translation, 50% rotation. So half of the potential energy goes into translation, half goes into rotation. The rotational energy goes into spinning the wheel. It's the translational energy that we're looking at to see who wins the race. So this kinetic energy translation wins or loses the race. Okay, so that's the one we're looking at in terms of the winner. And we see the winner here is the sphere, because 71% of the energy went into translational kinetic energy. And getting back to our fractions, the hoop, right, 1/2 is 0.5, 1/2 is 0.5, so that kind of matches up nicely. Here's where you have to be careful. Like 1/4, right, as a fraction is 0.25, but 0.25 is not the same as 33%. So don't just make them into decimals, right? Consider them to be a piece of the whole. So 1/4 is a piece of the whole. The whole is 3/4. 1/2 plus 1/4, right? 3/4 is the whole. 1/4 is 33% of it. So again, be careful with your fractions. All right, so the last example that we're going to consider is the example where we're not going down the hill, we're going to roll up the hill. So here, we are going to let the hoop roll up the incline, and we are going to look at using conservation of energy to handle this situation. So at the bottom of the incline, so my initial here is at the bottom, we are both rotating and translating because it's rolling without slipping. So we're rolling and translating. So we have the 1/2 I omega squared and the 1/2 mv squared. And that is then going to, that kinetic energy is going to be converted into mgh. And when it comes to a stop at this point, it has stopped rotating, so it comes to a stop, and it has stopped translating. So both are 0 when it gets to this point. Okay, and then we just have a little bit of algebra to do. It's a hoop, so our moment of inertia is our mr squared, and we can calculate very nicely the length along the incline. Remember, the h is the opposite, so we have sine theta equals opposite over hypotenuse. So when we solve for the h, we get L sine theta to put it in terms of our distance along the incline. And if the incline is frictionless, the distance along the incline now, notice, is half the distance. When we calculate the new distance, here we had V naught, let me zoom in here a little bit, V naught squared g sine theta is the distance along the incline. Now we have 1/2, right? So we have the 1/2 V naught squared g sine theta. And the reason that it doesn't go as high, not as much of the kinetic energy can be converted into potential energy, is because the incline, which is frictionless, never stops the rotation of the wheel. So even though the wheel is sliding up the incline, it is no longer rolling without slipping on the incline because the incline is frictionless, so it's just going to continue to spin. So the spinning here and the spinning here is the same spinning. So we're only taking the translational kinetic energy and converting it into potential energy in this case. So those are the examples you will have to work with for rolling without slipping in terms of energy and Newton's second law. So you have some nice examples in your notes now, I think, to help you problem solve. And we are going to move on to angular momentum.